So different shape gives different burning rate. So the inner, if it is fully inner circular, then it gives you progressive burning. If there is a slope like this, it burns from inner to outward and outward to inward. Because of that, we can get neutral burning type. And this one having various shape like devil anchor shape gives regressive burning. ምን መጥቷል እናየዋለን። ትንሽ ክላስ አለች። So this is various configuration of solid propellant rockets, motor, grain geometry. Actually, this is just grain geometry. Okay. So requirements of solid propellants. So propellant charge must meet variety of conflicting requirements. Means some of the propellants are maybe costly, or some of them are inefficient but low cost. So these conflicting requirements are there, but among them, the performance, we can see them from the point of performance from the point of practical application. So we can categorize them in that way. So from the performance standpoint, they should be burned inward at the burning surface. Means the burning should be from outward to inward. That means kind of regressive burning in a consistent and free, predictable manner. That is not unduly sensitive to pressure or bulk temperature at rate in 0.2 to 20 centimeter per second. That is called burning rate. The propellant burning rate should be lying between 0.2 to 20 centimeter per second. Propellant should be dense. It should be dense because we need to consume much propellant, means for long period of time. So it should be dense as much as possible to maximize the amount of propellant in a given motor size, while still producing reaction products of low molecular mass. So one of the requirement is density, but the reaction products should be with low molecular mass and high temperature. So that helps us to maximize the exhaust velocity. Another requirement is from the point of practical aspect, propellant must be insensitive to accidental ignition, especially this kind of, if it is sensitive, then it can be ignited by just in transportation means, from when we are moving it from place to place, it can be easily caught by fire and can cause damage to the whole design. So it should be insensitive to accidental ignition stimuli, and it should be amendable to self-manufacturing. One of very sensitive propellant is, for example, black powder. So if you make black powder, move black powder with some kind of metallic material, it easily caught by fire and it can easily be ignited. So that the safety aspect is one of an important consideration. Once they have been loaded in the motor, they must achieve and retain the mechanical properties which are necessary to maintain structural integrity under shipping. Shipping means placing, taking the vehicle from one place to another, storing it, and in some flight condition also. Since the energetic materials used in high performance propellants are often explosives, manufacturing the propellant is complex. It needs kind of complex technology. Okay? which involving special facilities and a strict safety guideline. We have to follow safety lines in order to manufacture this kind of propellant. So now the third component is the nozzle. So nozzle is one of an important part of the rocket, and it contains a subsonic region, that is continuously diverging region. It contains throat, and it contains supersonic region or divergent region. So in subsonic region, change in area is less than zero, means just this is the differential area condition. Mach is less than 1 here, okay? Because it is high pressure is there. Low velocity, high pressure region. Low velocity, high pressure region. This is transonic, or you can sonic point, you can call it throat. And then this is high velocity, low pressure region. This region, low pressure, high velocity region, so that it is Mach is greater than 1. So this is a simple constructional feature of nozzle. So the principal requirement for nozzle common to both solid and liquid is that it be able to produce supersonic flow of the exhaust gas from the combustion chamber pressure to the extra pressure. It is a function that is accomplished by proper countering, and this proper countering means providing proper shape to the nozzle and sizing the nozzle in proper manner. What will be the size of the subsonic region? What is the size of throat? What is the size of exit area? So considering this thing, we can achieve an optimal kind of nozzle. The contour is initially convergent, so this is convergent region to a throat, then it reaches to the narrow section known as throat, and then it is divergent here. Okay? The velocity of the gas in this region, in the divergent region, in the convergent region is equal to the velocity of sound. In the throat. The velocity of gas in the throat region is equal to the local velocity of sound, and the throat cross-sectional area controls the mass discharge rate. The mass flow rate, m dot, is controlled at throat. So this is the constructional feature of nozzle. Beyond the throat, the channel is divergent because, as you see, it is providing high velocity, low pressure region, that is, area is increasing. So that means the high velocity gas can accelerate through that region by supersonic speed. That is greater than Mach, with corresponding pressure decrease. So there is a pressure decrease there. Counters are often carefully designed so that inside the nozzle, shock waves and flow separations, which both degrades the thrust, do not form. So we have to consider this aspect also. The nozzle shock wave and the flow separation at the backside should be considered while we are designing nozzle. Okay, so these things can degrade the amount of thrust that we can obtain. Okay? And the detail of nozzle design depends strongly on application. So whatever we are designing, we have to consider the application, for which application we are using. Most applications require at least some of the insulations or special high temperature materials. Means when nozzle is constructed from some graphite material. If there is no graphite material, at least maraging steel should be there. This maraging steel is expensive type of steel actually, but it is abrasive resistant. Abrasive means erosion of the material particle when high velocity gas are passing through it. So maraging steel is strong and abrasive resistant. Graphite also is one of the material for very sensitive region of the nozzle. So in order to protect the load carrying structure from thermal failure, we must use this material. Many applications require that the direction of the exhaust flow by controllable over few degrees of order to provide steering mechanism. Some of the nozzles are providing some kind of movement that is known as steering. So steering mechanisms are also there for this. And this is accomplished in variety of ways that frequently complicate the design considerable. Yeah. Yeah. Huh? ትንሽ ጠብቀኝ ትንሽ ጊዜ አበባ ብዙ ነገር አምጥቷል እዚህ አበባ ብቻ እንትን አለ አሁን መጣል ዛሬ ነው ምኑ ለእኔ አልተነገረኝም Okay, sorry for. Okay, so the next important component of solid rocket motor is igniter. Igniter is the one that helps us to ignite the whole chemical. So igniter and solid rocket motor provide means of heating the surface of main propellant charge to high energy temperature to induce combustion, to induce an appropriate combustion. That is the intention of igniter. So at the same time, the igniter is usually designed to produce some initial pressure increase in the motor to assure more predictable startup. So ignition startup is the main thing. The overall design of the rocket depends on that initial startup. If there is failure, especially in solid rocket motor, if failure in the startup or an unappropriate ignition take place, then the whole system will be collapsed. The whole system will be end up. So in order to avoid such kind of catastrophic failure, we must consider an appropriate igniter. So the igniter consists of igniter container of metallic like metal oxidizer mixture. That is black powder is one of the igniter part. This black powder is highly sensitive material for sensitive in the sense it's easily caught by fire. Okay, so we have to take care for black powder igniter material. That is more easily and quickly ignited than the propellant. And it initiated by electrical skew. There we provide some electrical wires. And the electrical wire will be connected with kind of this what you call there is one easily sensible material known as mercury fulminate. There is a mercury fulminate flames. Filaments of mercury fulminates will be there. That easily helps us to initiate the ignition soon. So electrical wires are required. Igniter casing is required. So we have various types of igniters. Let's see. It will be very clear for you once you see that. Okay. Igniter case is designed to shield until fired and it disperses hot and burning products when pressurized by its own burning. Okay, so let's see various types of igniters. I think this is the igniter. There is igniter casing. Inside there, the sensitive kind of easily ignitable materials or chemicals are inside there. That igniting material is most of the time it is black powder and other types of chemicals. And we have this type of wires. This type of electrical wires which can easily get heated. Okay, so this is the quick starting up wires. So it can be chromium wire, it can be nickel wire. So nichrome, we call this these wires as nichrome, nickel chromium wire. Or sometimes instead of that, we can use mercury fulminate for the big rockets which are going to space stations or beyond that. Okay. So, so these ignition systems are two types usually. One is pyrogen igniter, another is pyrotechnic igniter. What are pyrogen, what are pyrotechnic, we can see. So solid rocket motor require an efficient ignition system to start its functioning, and a separate ignition system called igniter, which is assembled into the rocket motor to achieve the task. The task is igniting the inner surface of the propellant grain. So that is the task. So the two types are this. How we can differentiate them? Pyrotechnic igniter is one of the main igniter types. So in pyrotechnic igniter, we use pyrotechnic components or compositions, which are energetic propellants like chemical formulations in the form of pellet, in the form of granular, in the form of various shape, okay, which gives large burning surface area and within short time. Okay. The constituents of igniter charge, especially pyrotechnic igniter charges, are fuel, oxidizer, and binding agents. These three things are in a proportional manner. Fuel is there, oxidizer is there, and binder. The fuel, in the case of black powder, is the charcoal. Charcoal is considered as fuel. Potassium nitrate and sulfur are considered as another components. Okay? So powdered aluminium, powdered boron, powdered magnesium are used as fuel. Okay, charcoal also. Charcoal also is one of the part of this thing. Potassium nitrate for the potassium perchlorate, other like ammonium perchlorate, ammonium nitrate, which are also used as oxidizer in this case. And then the plasticizers are like ethyl cellulose, which are plasticized ethyl cellulose is used as binder. So binding agent, fuel, and oxidizer are required in proportional manner. So what you are looking here is a black powder ignition charge. This black powder ignition charge is charged, which is placed inside of this container, and the container is having a cap. This cap will come out, and then it is attached with some electrical means. The electrical wire will come out, and there is some nichrome wire, or unless on the otherwise we use mercury fulminate for that. So which finally prepared in this manner. So this is the igniters, pyrotechnic igniters. Okay. So these igniters are placed in the motor chamber in front of the propellant grain. And then when we are switching on electrical system, then it immediately, this one immediately burn out. And then the inner surface or the exposed surface of the propellant start to burn. That produce. So this is what we call pyrotechnic igniter. So ignition of solid rocket motor is a series of events. Within that, a series of events will take place in a tightly timed sequence, starting with the first sequence is application of an electrical pulse from electrical system. The second is initiation of first fire element. That is, a skew or pyro cartridge will initiate. And the third step is generation of flash or flame melt. And the fourth step is application of flash by primer. Primer means the heat start. And building up a flash to strong flame by main igniter charge. So it distributes immediately those flash or flames and to the main charge, that is propellant charge. Hence, a compressive, and for that we need an appropriate knowledge is required. Anyways, I didn't show it is not there. Anyways, let's see the pyrogen igniter. The second main component of igniter is pyrogen igniter. So this pyrogen igniter is for very big rockets. Okay, it is the first one. Pyrotechnic is for small rockets, but this by itself, this pyrogen igniter considered as a small rocket itself. So on that, these are the exploded drawing of pyrogen igniter components. Okay, it has some end cap, aft end cap. From this side, another end cap is there. Okay, there are containers. So it's by itself, it is a small rocket actually. Okay, so this is kind of exploded. This is 1/4 of or half section cross section of the igniter. And what you can see here are pyrogen attachments is here, attachment screws. Igniter leads are there. Nichrome igniter or nichrome wire is there. Ignition powder is there. Okay. Again, burst diagram is here, diaphragm. Yeah, okay, burst tape is there. Here, there is a burst tape. O-rings, the sealing materials. O-rings are there. Bulkhead is here. So these all are the constituent parts of pyrogen igniter. So still the general requirement of an igniter, the temperature of propellant surface should be raised above it is auto ignition temperature. Motor chamber pressure should be raised above threshold pressure requirement for suitable burning. Ignition delay time, that is the time delay for application of an electrical pulse to point where 10% of motor peak pressure is achieved. So igniters must provide about 10% of the pressure of motor peak pressure. Okay, so the rate of pressure rise, dP over dt, that is the rate of pressure rise in the motor chamber during ignition transient should not be unduly high, leading to unstable peak shock. So the ignition should satisfy the functional, environmental, and self-life or a stronger requirement. So these are some of the requirements. And the next important component is insulation. Okay, insulation are materials. These insulators are materials which protect heat transfer from the motor chamber to the external surface of the rocket itself. So an insulation in solid rocket motor is the layer of heat protection materials placed in between the internal surface of the casing material and the exposed external surface of the burning propellant. So this material is a material with high heat resistance, unless the insulation itself can burn. So it is heat resistant material. The high temperature of propellant combustion gas inside solid rocket motor ranging from 2000 to some 300, 500. This is combustion chamber temperature actually, which needs a thermal protection system. So this insulator is most of the time made from ethylene propylene diene monomer, EPDM. So this is EPDM is the most common insulation material. Okay. Yeah, this is the same thing what we have discussed before. So just where I'm summarizing the whole thing what we have discussed on solid rocket motor. So solid rocket motor consists solid rocket motor case. It consists of igniter. It consists nozzle. It consists solid propellant, and it consists insulation material. Okay, so these all are here. Okay, so I think this is fine for today. If you have any question on today's lecture, we can discuss. Hello?
አቤት አቤት እየሰማን ነው ዶክተር።
ጥያቄ ካላችሁ እንትን እንላለን። ለዛሬ ትንሽ ቢዚ ያደረጉ ስራዎች ስላሉ እዚህ ይበቃናል።
ኦኬ ኦኬ ዶክተር በቃ
ጥያቄ ያለው አለ?
እንትኑ ላይ ዶክተር ኖዝል ዲዛይኑ ላይ ዲዛይን የምናደርገው ለሶሊድ ፕሮፔላንት ሮኬት ነው። ለሶሊድ ፕሮፔላንት ሮኬት ሞተር እሺ በቃ
ማለት ይሄ አሁን እኛ ለምን ለእንትኑ ቀላሉ እሱ ስለሆነ እናንተ አሁን እንድትሰሩ ነው የሚፈልገው። ምንድነው ሶሊድ ሮኬት ሞተርን ዲዛይን ካረጋችሁ ሌላው ምንም የተለየ ነገር የለውም። እነዚህ ፓይሎት and other things will be የዛ ኮንቲኔሽን ነው። ስለዚህ ስሞል ሞዴል ሮኬት መስራት ትችላላችሁ ማለት ነው። አሁን ምንድነው ፕሮፔላንቱን ካወቃችሁ የፕሮፔላንቱን ባህሪ የፕሮፔላንቱን ዲዛይን ኮንፊግሬሽኑ ወይም ደግሞ ሼፑን ካወቃችሁ በዛ ፕሮፔላንት ተነስታችሁ ስሞል ሮኬት ማኑፋክቸር ወይም ደግሞ ፕሮዲዩስ ማድረግ ይቻላል። ምንም የሚከብደን ነገር የለም። ቢያንስ የሆነ 2 ኪሎ ማን ነው አንድ 5 እስከ 5 ኪሎ ሜትር ሊሄድ የሚችል from simple chemical መስራት እንችላለን። ስለዚህ ለዛ የሚሆን ምንድነው እነዚህን ዋን ቱ ዋን ካወቃችሁ ነው። ያን ካላወቃችሁ መስራት አትችሉም። ኢግናይተሩን ማወቅ መቻል አለባችሁ። ፕሮፔላንት ግሬን ካራክተሪስቲክስን የኢግናይተር ካራክተሪስቲክስም ያስፈልጋል። ኤኒዌይስ አቬይለብል በሆኑ ፕሮፔላንቶች አቬይለብል በሆኑ ኢግናይተር መስራትም ይቻላል። ብዙ ኢግናይተርን ከብላክ ፓውደር ኬሚካል መስራት ይቻላል። ዘን አፍተር ትሮት ዲዛይን ነው ክሪቲካል ኢሹ። ኦኬ ትሮት ዲዛይን ማን ነው ኖዝል ዲዛይን ነው። ዘን ኬዚንግ ዲዛይን እነዚህን ሁሉ ኢንክሎዝ የሚያደርግ ነገር ስለሆነ ኬዚንግ ቢሄቪየርን ቼክ አድርገን እንትን ማድረግ እንችላለን። ኦኬ you see nozzle throat insertion, this nozzle throat insertion is from very strong material, erosion protect በሚያደርግ ነው። ለምን እዚህ ጋር ከፍተኛ የሆነ erosion እንትን ያደርጋል። ስለዚህ እዚህ አካባቢ እነዛ ውድ ቢሆኑም ግራፋይት ወይም ደግሞ ማራጂንግ ስቲል የምንጠቀመው እዚህ አካባቢ ነው፣ ኖዝል ትሮት ኢንዘርሽን አካባቢ። ስለዚህ appropriate shape ኖዝል ሼፕ ካመጣችሁ እንትኑን የጠበቀ ማለት ነው። so that is the main point። ከዛ በኋላ ያለው ምንድነው የኤሮዳይናሚክስ ሼፕ ዲዛይን ነው። ከፊት ለፊት ከዚህ በኋላ ምን ጨምረው ምንድነው ፍሮንት ዱም ነው። ፍሮንት የእንትኑን ሼፕ ማምጣት ነው። አስፈላጊ ሲሆን ፊንስ and other aerodynamic shapes will become okay so the main በቃ ሮኬት የምንለው ይሄ ሞተሩ ነው። ሄሎ
ሄሎ ሄሎ ሄሎ ጥያቄ ስለነበረኝ ነው።
ኦኬ
ሶ ምናልባት ዲዛይን ስናረጋው የስፔሲፊኬሽን ኦር ምናልባት ቅድም እንዳሉት ምን ያክል ኪሎ ሜትር ሊሄድ ይችላል የሚለውን አንዳንድ ምንድነው የምናደርግበትን ፓራሜትሮች ስፔሲፊኬሽን ቢኖረን ጥሩ ነው። ምክንያቱም ሁሉም ነገር ዲፔንድ ያደርጋል። ለምሳሌ ወደ ላይ የሚሄድበትን ርቀት ማናቅ ከሆነ የዲዛይን የኖዝላችንን ኢቭን የተለያዩ ዳይሜንሽኖችን ለማውጣት ይከብዳል እና አትሊስት ቤዚክ የሚባሉ እንትኖችን ቢነገረን እና እዛ ላይ መሰረት አድርገን ሞዴል ብናደርግ ጥሩ ነው ብዬ አስባለሁ።
ማለት ትራጀክተሪውን ዲዛይን ማለት ነው። ያ ማለት ቤዚካሊ አሁን available በሆኑ ኬሚካሎች በእኛ በዚህ በፕሮፔላንት የሚወሰን ነው። ፕሮፔላንታችን ምን አይነት ባህሪ ያለው ሳይዝ ውስጥ ምን ያክል ፕሮፔላንት ነው የምንጠቀመው ለዚች ለፓርቲኩላር ለምሳሌ ለትሬኒንግ ወይም ለእንደዚህ ሲምፕል ኤክስፐሪመንታል የሆነ ኪሎ ሜትር ዲሳይድ አድርገን ለዛ የሚውለውን ፕሮፔላንት ካወቅን ዘንድ የሚቀረው ምንድነው የስትራክቸራል ዲዛይን ፓርት ነው። ፕሮፐር የሆነ ኤሮዳይናሚክ ሼፕ ከያዘ ያን ኢንተንትድ የሆነ ሬንጅን ከቨር ያደርጋል። አንለስ ሌሎች ፓራሜትሮችም አሉ። አሁን ኢግኒሽን ስታርታፕም የራሱ የሆነ እንትን አለው። ፕሮፐርሊ ኢግኒሽን ላይ ሰፊሸንት የሆነ ኤነርጂ ካገኘ የተባለውን ሬንጅ ይደርስልናል። ግን ሜንሊ አሁን የፕሮፔላንት ባህሪ ነው የሚወስነው። ከፕሮፔላንት ባህሪ የፕሮፔላንት ኢንተርናል ኮምበስሽን ቻምበር ፍሪ ቮሊዩም ኤነርጀቲክ ፕሮፐርቲ ኦፍ ዘ ፕሮፔላንት እነዚህ በጣም ፋክተር አላቸው። ዘን አፍተር የተለያዩ ኤሮዳይናሚክ ሼፕ ላይ የምንጨምራቸው ነገሮች ካሉ እነዛም የራሳቸው የሆነ ድራግ ፎርስ የመፍጠር አቅም ስላላቸው የተፈለገው ሬንጅ ላይ ደርስልን ይችላል። ስለዚህ ስሞዝ ኤሮዳይናሚክ ሼፕ እንሰጣለን። ዘን አፍተር አፕሮፕሪየት የሆነ ኢግናይተር ዲዛይን እናደርጋለን። appropriate የሆነ ፕሮፔላንት ከተጠቀምን be sure that it will achieve the range. So your space trajectory ዲዛይን የምታደርገው ከሚታወቁ ፓራሜትሮች ተነስተ ነው። እነዛ ፓራሜትሮች ባልታወቁ ሁኔታ ስፔስ ትራጀክተሪ ዲዛይን ባደረገው ምንም ትርጉም አይኖረው። ግን ያው ይሄኛው ስፔስም ምናምን ስላልሆነ እዚሁ ዊዝን አትሞስፌር ስለሆነ አትሞስፌር ላይ ያሉ የአትሞስፌሪክ ሬዚስታንስ ድራግ ፎርስ እነዚህ የኤሮዳይናሚክ ሼፖች የሚያመጧቸው ፋክተሮችን ኮንሲደር ማድረግ መቻል አለብንና በእንደዛ ማወቅ ይቻላል።
ያ ሶ ምንድነው አንዳንድ አሳምፕሽኖችን በራሳችን ኮመን ከሚባሉ ኮመን የሚባሉ አሳምፕሽኖችን
at any design point at any point of design there is engineering assumptions. proper የሆነ አሳምፕሽኖችን መጀመሪያ ዲተርማይኒንግ ፋክተሮቹ ምንድናቸው? ይሄን ሪታርድ ሊያደርጉ የሚችሉ ምንድናቸው? አክሰለሬት ሊያደርግ የሚችለው ምንድነው? እየተጠቀምን ያለነው ፕሮፔላንት ምን ያክል ኤነርጀቲክ ነው? ምን ያክል ሊያስኬድ ይችላል? ፕሮፔላንት ፕሮፐርሊ ካለ እኮ ይቀጥላል ሙቭመንቱን። ስለዚህ በተለይ ደግሞ ኖዝል ትሮት ዲዛይን is one of the parameters. Nozzle, not only nozzle throat but nozzle exit area, how much it expands, how much it contracts. If it is expandable nozzle ከሆነ እንዴት ነው የሚሆን? ፊክስድ መሆን ይችላል፣ ግን ያ ፊክስዱ ካራክተሪስቲክሱ ምንድነው? ስለዚህ እያንዳንዱ ፖይንት ላይ ካልኩሌሽን ይሰራል። የተርሞዳይናሚክ ካልኩሌሽኖች ይሰራሉ። አሁን ተርሞዳይናሚክ ፓርቱን አልደረስንም፣ እንትን ያልን አይደለም። እያንዳንዱ ሴክሽን ላይ what is the thermodynamic behavior በኮምበስሽን ቻምበር ላይ ያለው thermodynamic behavior at throat ላይ ያለው thermodynamic behavior at exit ላይ ያለው thermodynamic behavior አለ። እነዚህን thermodynamic behavior ካጠናን በኋላ የማግኘት የምንችለውን ትራስት አውቀናል ማለት ነው። በእነዚህ ላይ ገብቷል። የትራስት ፎርስን ካወቅን ያ ትራስት ፎርስ ምን ያክል ሊጓዝ እንደሚችል ደግሞ ካልኩሌት አድርገን የግሬን ሬት ኦፍ ኢትስ ባርን ሬት ግሬን ባርን ሬትም ማወቅ መቻል አለብን። የሰጠነው ግሬን ምን ያክል መቆየት እንደሚችል ግሬን ባርን ሬት ምንድነው የሚያሳየው? r is equals to a times p the power of n አሁን ስላልደረስናቸው ነው። ስለዚህ እነዛ ነገሮች ዲተርማይን አድርጋለሁ ማለት ነው።
ኦልራይት
ክሊር ኦኬ። ሶ የሚመቻችሁ ሰዓት ንገሩኝና ቅዳሜም እኮ መሆን ይችላል በነገራችን ላይ
ምናልክ ዶክተር
የሚመቻችሁን ቀን ቅዳሜም ይሁን እሁድም ይሁን እንደዚሁ የምንገናኝበት ንገሩን። ስለዚህ በእንደዛ አይነት እንሄዳለን።
እኛማ ማክሰኞ ነበር የመረጥነው አንተ አልተመቸህም መሰለኝ እንጂ
ማክሰኞ አልተመቸኝም ነበር። አዎ
ከሰዓት ምናምንም
ብቻ አሳውቁኝ። በቃ ችግር የለም ለሁሉም።
እሺ ዶክተር።
እሺ ኦኬ። መልካም ቀን።
እሺ መልካም በዓል። ቻው።
ኦኬ ለሁላችንም።